Friends, today we will study dynamic equivalents for large scale systems. We know that the stability studies is one of the most fundamental and important study to be performed for system expansion planning, for design of the system, for operation and control also. Now, to solve actually the stability problem, what is to be done is that we have to develop the model of the system and then solve these equations using numerical techniques. Further, we require actually a large number of stability studies to be performed, and since there is no analytical explicit solution, one has to resort to the numerical techniques. Now, these numerical techniques take lot of time to obtain the solution. Further, the size of the system has become very large, and therefore, when the size of the system becomes very large, we will have a mathematical model of very large dimension or very high dimension, and therefore, there are two problems. One is actually that the dimension of the mathematical model of the system. Another is the time which is required by using the numerical techniques. And in practical situation, it is practically impossible to represent the entire system in detail, and therefore, there is a necessity to resort to some equivalency. Now, here when you talk about the equivalencing, the basic philosophy is something like this, that whenever a disturbance occur in a particular portion of the system, then that portion of the system which is very close to the disturbance is severely affected, while the system which is away from the disturbance is lesser affected, right, and the system which is very far away may have very little effect on the system, and therefore, one can represent the part of the system which is very close to the location of the disturbance in detail, and the system which is away can be represented by an equivalent. However, actually the system which is not that severely affected, but affected to some extent, right, it has an effect on the dynamics of the machines in the steady portion, right, and therefore, there is a necessity to adequately capture the dynamics of the system which is away from the steady system, right, and therefore, what we do here is that whenever the system large system stability analysis is to be performed, right, we divide the system into steady system, external system, and third portion we call it is a remaining system. Now, to understand what we mean by steady system or external system or the remaining system, let us just take this small system. It has a number of generators. You can see here actually in this diagram, there is a number of buses. I have not shown the loads, but a number of buses, the loads are connected. Now, suppose I am interested in studying the behavior of this portion of the system. Let us say that this is the portion in which I am interested, right. It was my interest is to know if there is a fault in this portion of the system, right, what will be the dynamic behavior of the system. Therefore, what we do is that we call this portion as a steady system. Steady system. Now, to this steady system we have system outside the steady system. Now, some portion of this system which is outside the steady system has significant influence on the dynamics of the steady system. We will represent this by, we call it the external system. External system. Then beyond this external system we have this portion. This can be given the name as remaining system. You can call this as a remaining system. The philosophy here is that we are interested in the behavior of the system whenever there is a fault occurs in this portion of the system, dynamic behavior of the system, and to know the tangent stability solution of this system. Then what is to be done is that this external system should be represented by an equivalent. Okay? While representing the external system by the equivalent, this equivalent should be accurate enough so that we capture adequately and accurately the effect of this system on the steady system. Okay? Similarly, the remaining system is very far off from the steady system and it has very little influence on the dynamic of the steady system, then this can be represented by approximate equivalent, very approximate equivalent, or we can say very simplified model we can represent it. Okay. Many times the system can be divided into two parts only, steady system, external system, may not have remaining system. Now, here you can just see these two buses at which the external system is connected to the steady system, right. Now, these two buses or these buses where steady system is connected to the external system, we denote these buses as boundary buses. That you can say that this bus, these are boundary buses, boundary buses. Similarly, for this external system, right, the buses, for example, this bus or this bus where actually the external system is connected to the steady system, we call these as terminal buses. These buses will be called at the terminal buses. Okay. Now, over the years, I can say at least during the last 4 decades, efforts have been made to develop dynamic equivalents. Okay. Now, when we develop the dynamic equivalents, we have to ensure two things. One is that the equivalent is accurate enough so that we capture the effect of this equivalent on the steady system adequately. Second is that when we obtain the equivalent, the process of obtaining the equivalent should be very fast. That is, there is a mathematical way or there is a methodology which is used for obtaining the equivalent for the system, and therefore, the time which is required or computations which are required for obtaining the equivalent of the external system should be reasonable. Okay. Now, many times we may require some more time to obtain the equivalent, but since we may have to perform many stability studies, right, and if we use this equivalent, then whatsoever time you spend in obtaining the equivalent is compensated, because actually in practice when you solve the stability of the steady system using the equivalent, right, and equivalent is to be obtained only once, right, and therefore, when you do the multiple stability studies, that whatsoever time which is required is compensated for this. In fact, the literature on this dynamic equivalence is very vast, and we will confine to only few techniques which are quite, you can say, popular and used in practice. The techniques are classified under these three categories. That is the dynamic equivalence techniques. We can say, or we can classify broadly in these three categories. Number one, dynamic equivalence based on distribution factors. Dynamic equivalence based on distribution factors. The second technique is based on modal analysis and order reduction. Modal analysis and order reduction. And the third technique is known as the coherency based dynamic equivalencing technique. There are three techniques. On each technique you will find lot of literature in the published. Okay. Recently people have developed techniques which are called actually the modal coherency based techniques. That is, they take the advantage of the modal equivalencing technique and the coherency based equivalencing technique also. Right. The dynamic equivalents which are obtained using the distribution factors, right, is a simplest of all the techniques. In this arrangement, what is done is that this whole external system, including the remaining system, is represented by an equivalent generator connected at the boundary buses. That is, suppose there are two boundary buses, right. At these two boundary buses you connect two equivalent generators, right, and if you have number of loads also, then you represent by two equivalent loads, right. So that when you perform the stability study, you have to perform the stability study of this steady system. For example, in this steady system, now you will have two generators which are there already and two equivalent generators, right. But this technique is based upon some heuristic approach. It is not having very sound mathematical base, right. Now, earlier when the computers of very limited capacities were available, then this was the best approach for obtaining the equivalence. But now, since we have better computing facilities available, right, therefore, another techniques have been considered, and they are having a sound mathematical base. Okay. We will deal with this. I will just mention about this modal analysis technique. In this modal analysis technique, basically the first one has to obtain for the complete system linear model. One is to obtain linear model. With this linear model you obtain the eigenvalues of the system, okay, and then using this information about the eigenvalues you eliminate certain modes, okay, and then retain only those modes which have a significant influence on the system dynamic behavior. Okay. There may be some modes which decay fast, you can just ignore them. Those modes which are very high, very low time constant actually, and those modes which have high time constant, you retain them. Okay. Because we are studying actually the stability, this is a slow phenomena. Okay. Because we always do actually in 2 seconds, 3 seconds, and wherever you have actually the time constant of the modes which decay very fast in say a fraction of a second, you can ignore. The major drawback of this model equivalencing technique is that one has to obtain the eigenvalues of the large system and then eliminate or reduce actually the dimension of the system. This is what it is. Now, one very serious problem which comes here is that this reduced order model, you cannot actually correlate each mode with the physical system. You can appreciate this point actually, that there is a certain physical system, right, and with this, and you have obtained actually reduced order model using this model analysis. Then this reduced order model, right, you cannot have one to one correlationship between the model and the physical system. And in view of this, we shall be discussing mainly this coherency based dynamic equivalent, okay. And in this coherency based dynamic equivalence, when we study, first let us see what we mean by coherency based dynamic equivalence. I think I can first tell you what is the definition of coherent group of generators. The definition is like this: a coherent group of generating units for a given perturbation is a group of generators oscillating with the same angular speed and with terminal voltages in a constant complex ratio. This definition we have to very clearly understand. That is, in a power system you have a large number of generators, okay. Whenever a particular disturbance occurs, okay, then you will find actually that a group of machines swing together, right, they all swing together. It means when you plot actually the delta versus time or the swing curves, then those machines which have the identical swing curves, right, form a coherent group of machines, okay. And therefore, if we can identify for a particular system the coherent group of machines, then we can replace the coherent group by one equivalent machine, right. And this is a very sound mathematical technique. That is, yes, there is a system where whenever you give a perturbation, the machines which swing together, which have the identical swing curves, right, they form a coherent group, and this coherent group can be replaced by an equivalent machine. That is, when you talk about the angular speeds, they all have the same angular speed, okay. However, the terminal voltages of these machines, right, will maintain a constant complex ratio, okay. Now, when we want to obtain dynamic equivalence using coherency technique, then there are three important steps which are involved. The first step is identification of group of coherent generators. Obviously, that before I replace the system by equivalent, I should know that, okay, these machines are coherent, these machines are coherent, these machines are coherent, and groups have to be obtained. This is the first step. And second step is called network reduction. The terminal buses of each group of the coherent generators are replaced by a single equivalent bus. You try to appreciate this point, that suppose the first step is that we have done some study and identified that, okay, these machines form a coherent group, okay. Then each machine has connected to a bus, okay. Therefore, what is to be done is that we have to do network reduction and obtain an equivalent bus where all the machines are connected, okay. So that once they suppose take an example that if I find that machine number 1, 3 and let us say 6, right, they form a coherent group. Then I want to, all these three machines will have their buses, they are different buses at which they are connected. Okay. But we want to replace this by one equivalent bus where all these machines will be connected in parallel, and then these machines will be replaced by one equivalent. Is it clear? This is the second step. And the third step is called dynamic aggregation. The dynamic aggregation means once you have obtained a common bus at which all the machines which form a coherent group are connected, right, then we represent equivalent machine by what is called a dynamic aggregation phenomena, which will have equivalent inertia constant, equivalent excitation system, equivalent turbine governor model, equivalent tangent reactance, and so on. It means this is a very important step where you obtain an equivalent. Now, we can understand that these are the three important steps which are involved. That is, you have to first identify the coherent group of generators, and these are the other two steps. Now, here to identify the coherent group of generators, we have a very important reference. That reference is, the paper is written by Robin Padmore. The title of the paper is Identification of Coherent Generators for Dynamic Equivalents. That emphasis is for identification of coherent generators for dynamic equivalents. This paper has appeared in IEEE Transaction on Power Apparatus and Systems, volume PS 97, number 4, July August 1978. There is another paper, there is G. J. Berg and A. Gafurian, representation of coherency based equivalents in tangent stability studies. This has appeared in Electric Power System Research, volume 6, which is in 1983, pages are 235 to 241. Today, we will concentrate on identification of coherent generators for dynamic equivalents. Okay? And then in the next lecture, we will talk about the other two aspects, that is network reduction and dynamic aggregation. And there is one more research paper which deals with dynamic aggregation, that I will tell you in the next term. Now, here when we talk about identification of coherent group of generators, let us see what is the simplest technique. How to identify? Can you tell me how to identify the coherent group of generators? Because you know what we mean by coherent group, or what is the meaning of coherency.
By respect on the swing curve of each individual generator, identical swing curve will give the coherence.
The response of the class is that we first obtain the swing curves of all the machines, right, and those swing curves which are identical, we group into one coherent group, and similarly other coherent group. It means we have to first perform a detailed tangent stability analysis. You have to take a system and you perform a detailed tangent stability analysis, okay, and then you can group them. This is one technique, which is a straightforward and accurate technique. However, there are certain facts which have been obtained through lot of research work. The facts are like this, and these facts can be used to obtain the approximate swing curves for identifying the coherent groups of machines. Instead of going for the detailed tangent stability analysis, using these facts we can obtain the approximate swing curves, right, and we can find out the coherent group of machines, and these can be used actually to finally obtain the equivalent. The assumptions, the facts are like this, they are assumptions as well as actually the facts. The coherent group of generators are independent of size of disturbance. Coherent groups of generators are independent of size of disturbance. This is a very important point here. That is, if at a particular bus, right, if a fault occurs, whether the disturbance is of say 0.1 second duration or whether it is of 0.2 second duration, because the size of disturbance will depend upon the duration of the disturbance to which the system is subjected. For example, if you take three-phase fault at a particular bus, right, if the fault persists for more time, then it is a bigger disturbance. If suppose fault persists for very short time, it is a disturbance of small magnitude. Because if you suppose somebody performed the study that okay, you consider disturbance and study the dynamic behavior considering the different fault clearing time. It means you are basically studying the behavior of the system with varying magnitude of disturbance. Now, suppose you consider actually the three-phase fault or say unsymmetrical fault, right. The unsymmetrical fault is less severe as compared to three-phase fault, right, and therefore, from that point of view, the one very important conclusion here is that it is independent of size of disturbance, and therefore, coherency can be determined by considering a linearized system. That is, you can obtain the coherency behavior using a linearized system. Okay. This is one very important, and on this basis we can get actually the coherency behavior or coherent groups very quickly. The second assumption is or fact is that the coherent groups are independent of the amount of details in the generating unit models. That is, if you look here, that is, the coherent groups are independent of the amount of details in the generating unit models. That is, whether I model a generator by classical model or I model using the detailed model considering the amortizers, field winding dynamics, excitation system, turbine, right. The coherency behavior is same, and therefore, what can we do? We can use actually for coherency identification as simplified model, classical model. Why should I go for all detailed model, right? And therefore, the point is that one can use a simplified model. That is, therefore, a classical synchronous machine model is considered and excitation system and turbine models are ignored. Right? However, with these two important assumptions, right, but these assumptions have been verified by doing number of studies, okay, and these assumptions are valid to a large extent. Okay. And therefore, what we will study here today is that how to identify the coherent group of generators making use of these basic assumptions. That is, we will represent each machine by a classical model and we will use a linearized model to obtain the swing curve. Okay. Therefore, now if I write down the swing equation for a ith machine, for an ith machine considering small perturbation, okay, this equation is written as mi d by dt of delta omega I equal to pmi delta pmi minus delta pi minus di delta omega. Okay. Now, this term is to take care of damping which is present in the system, that is di delta omega I is a damping term. The second equation is d by dt of delta delta I, that is 2 pi f for the omega naught into delta omega I. Now, here m I is equal to 2 h I, 2 h I, and the speed deviation, that is delta omega I, right, they are represented in per unit. Okay. That is this is all what you know it. The next step will be that we write down the model of the network. Now, here small perturbation model for the network can be represented like this. I can, because here we will have number of buses, okay, and we will classify the buses into two categories. One is internal buses of the generator, internal buses, and load buses. Here we will not resort to any you can say elimination of nodes. Nodes will remain where they are. Okay. Therefore, you can write down the equation here, delta P G delta P L delta Q G and delta Q L as delta P G divided by delta 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 P G divided by delta theta. I will explain delta and theta. Delta P G by delta E delta P G divided by delta V. Second term will be delta P L by delta 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 P L by delta theta delta P L by delta E delta P L divided by delta V. The third row is delta Q G divided by delta 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 Q G by delta theta delta Q G divided by delta E and delta Q G divided by delta V. Last will be delta Q L divided by delta 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 Q L divided by delta theta delta Q L divided by delta E delta Q L divided by delta V. Okay. Multiply by a vector called correction vector, that is delta 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 theta delta E and delta V. That is for any network, right? We can write down the equation of this form, but this is basically the Jacobian of the network. This is the Jacobian of the network. Now, here delta, because here we will talk about the two types of voltages which are the internal voltage of the generator. are representing by generator by classical model internal voltage of generator. I will denote this internal voltage by the symbol E, right, and this E is a vector which will have the terms E1, E2 up to En depending upon number of generators. V is the voltage of the load buses, right. Delta is the phase angle of internal voltage and theta is the phase angle of voltage of the load buses, right. Delta Pg is the generator injected power. Okay. Similarly, delta PL and delta QL, these are the load bus residuals, and delta QG is similarly the deviation in generator power. Okay. Now, here in this model, once we represent the generated by classical model, okay, then what about this delta E? If we represent the generator by a classical model, then the internal voltage of the generator is constant, magnitude of the internal voltage is constant, and therefore, for classical model delta E is 0. Okay. Second point, what we do here in this case is that the effect of variation of load bus voltages on the delta Pg and delta PL is negligible. That is, the power transfers mainly depend upon actually the angle delta. That is, we know actually this decoupling, there exists a decoupling, right, and therefore, you can simplify this model and you can represent the delta Pg and delta PL in terms of these two quantities. That is, when you simplify this, when delta E is anyway 0 and these generations, these quantities hardly depend upon delta V. Okay. Therefore, with this assumption or assuming this decoupling, right, we can have a simplified model. The simplified model can be written here as delta Pg and delta PL as delta Pg divided by delta put delta Pg divided by delta theta, delta PL divided by delta and delta PL divided by delta theta. That is, we will use in our study this simplified model. Now, here I wanted to emphasize that this delta PL, that is the we call actually the load bus residual power, right. This delta PL is also 0 in normal case situations. We will use this term delta PL to simulate certain type of disturbance. To simulate certain, I will just explain. To simulate certain type of disturbance, we will represent this term delta PL will come into picture. Okay. Now, in order to represent these disturbances, because we will come across the different type of disturbances, right, and we can represent these disturbances in a very simplified manner. Let us first consider actually the a fault occurs in the system. And how do we represent the fault? Again, since we are trying to do some simplifications, let us say that how do we represent a fault, and that is represent the system during fault condition, let us say. Now, if you see very carefully, then during fault condition, during fault condition, since the duration of fault is small, maybe 2 cycles, 3 cycles, 4 cycles, okay, the normal fault duration which the system can withstand is of the order of few cycles. Okay. Now, during this period, the change in delta is small, that is when you look at the system as a whole, right. When the fault occurs, the system is subjected to acceleration, okay, and the delta, the rotor angles change. But during this period of about 0.1 second, which is a short duration of during fault condition, the variation in delta is not very large. Do you agree with this? If you just try to, you can say, visualize the equilibrium criteria of stability, right, then during the fault condition, if you see the change in delta, it is there, but it is not very large. Further, since delta is has varied over a small range or small variation is there, therefore, the acceleration, rotor accelerations at the inception of fault and the rotor acceleration at the fault clearing time, that is the accelerating power at the inception of fault and at the instant of clearing the fault, there is hardly any significant difference. You appreciate this point? That is, let us say I am just taking a single machine finite bus system. Okay. Let us say when the fault occurs, say before the occurrence of fault, the mechanical input say 0.8 per unit. The moment the fault occurs, the electrical output becomes from 0.8 to let us say 0.3. Okay. Therefore, the accelerating power at the inception of the fault is 0.5 per unit, is 0.8 minus 0.3. This is the accelerating power. Now, at the instant of clearing the fault, right, mechanical input is same. Let us say electrical output instead of being 0.3, let us say it is 0.31, because you are moving on the during the fault power angle characteristic. Therefore, the acceleration power or accelerating power is 0.8 minus 0.31, that is say 0.49. Therefore, we can make an assumption that okay, during this fault, the acceleration power remains at the level of say 0.5, and we will not create any big error, small error will be there, but still actually. And therefore, this situation can be simulated by increasing the mechanical input by 0.5 for that particular period. My mechanical input was initially say 0.8, I increase in my model mechanical input by that much amount, okay, and then the system behavior or dynamics is not going to be affected, it remains same. Therefore, in this case I have not to can say obtain the mathematical model during the fault condition. I have to simply increase the mechanical input by that much amount, right. This is the one way simply you can say simulating the fault condition, right. Now, suppose you have a situation where I am just taking an example, simple example. Let us say that you have a system, a simple system with 2 generators and 3 buses like this. Let us call this is bus number 1, bus 2 and say bus 3, a simple system. Now, suppose I want to consider a disturbance where this line connecting bus 2 and 3 is tripped. The line connecting bus 2 and 3 is tripped. One simple way is that okay, I obtain actually the model, right, considering this post fault or post tripping situation. Another way of simulating will be that okay, you look before the occurrence of fault, what was the power which was flowing on this line. Let us say I am just showing here that of course I am putting opposite arrows. Let us say the power at this point which are entering this bus I call as P2, and power entering at this bus is called P3 because of this line connection. For example, if suppose you consider a lossless line right. If P 2 is say 50 megawatt, P 3 will be minus 50 megawatt. Okay. Then this particular situation can be represented that is, at this bus I inject a power equal to P 3, I inject a power equal to P 2 at this bus. Therefore, these two, this condition and this condition, they are same. Okay. Now, I can simulate the tripping of the line 2 3 by setting P 3 equal to 0 and P 2 equal to 0. Okay. Now, once I say that P 3 equal to 0 means what is the change in the load power? It has changed from P 3 to 0. Therefore, delta P L will represent actually this disturbance here, that is at this bus number 3, whatsoever is the change in the power, right, that I put in my model delta P L equal to so much. Similarly, for P 2 I represent actually as change in delta P L, because this delta P L which I am trying to say is a vector where all the load buses are considered. Therefore, here in this particular case these two entries, right, I will make P 2 and P 3 to represent the line tripping, right. Therefore, when you are trying to take a particular fault condition or line tripping condition, or even you can consider actually the generator tripping, you have not to change your model. The network model remains same, and by just you can say changing the values of delta P L or delta QG, I am sorry PG, you can change the condition of the fault, or can simulate the condition of fault, right. Now, the question basically is that how do we obtain the swing curve considering this type of situation. Now, here you can easily see that in this model this delta P L and can be is basically to simulate a particular type of disturbance. Okay. Now, to solve this problem, we again start with these two set of equations. First is our linearized differential equation, second is the network model. Okay. With this linearized differential equation network model, what we do is that you apply the trapezoidal rule of integration to convert this linear differential equation into an algebraic equation. Okay. I will write down this step. That is, I have the equation of the form which I will integrate both the sides. Okay. I will have this equation m I integral d omega I by dt. This is equal to we have termed delta P m I dt minus integral delta P E I dt minus d I is constant integral delta omega I. Okay. We will integrate this equation over a time interval delta t, okay, over time integral delta t, applying the trapezoid rule of integration. Now, following the convention given in the reference paper, I will start like this, that we will integrate over the time interval t minus delta t to t. One can take t to t plus delta t, but I am following the same convention which is given in the reference paper, okay, t minus delta t to t. Let us write down the value of this integral. It will be m I into delta omega I t minus delta omega I t minus delta t. Okay. So, for this term is concerned, when I integrate this over this time integral, I will get delta omega I t minus delta omega I t minus delta t. Now, here this term delta P m I, this delta P m I is the change in mechanical power. Okay. Now, we use this term to simulate the type of fault. Suppose you are considering a fault and you are trying to simulate the fault by increasing the mechanical power by some amount, which will be equal to the accelerating power at the instant of occurrence of fault. Therefore, delta P m I will remain constant, Therefore, what will the integral of this? Delta P m I, of course, it is constant, I am saying as a function of t. Why I am saying it is a function of t? Because when the fault is cleared, its value has to be changed. Once the fault is cleared, okay, then post fault system is going to be different. That I am putting this as a function of t, okay, but it will remain whatsoever is there, it is remain over particular time. This into delta, okay, minus what will be the integral of this by applying the trapezoid rule of integration? Delta t by 2, which is the multiplied by delta t by 2 multiplied by delta P E I t minus delta t plus delta P E I t, okay. Here you can use this term, right. Then one more term is there, minus d I delta omega I t minus delta t plus delta omega I t multiplied by delta t by 2, okay. That is the first differential equation is integrated over a time interval t minus delta t to t, and we get actually an equation applying the trapezoid rule of integration. This is algebraic equation. Similarly, you take the second equation. When you integrate the second equation, you will get delta delta I t minus delta I t minus delta t equal to 2 pi f naught, that remains same. You will have the term delta omega I t minus delta t plus delta omega I t into delta t by 2. Now, both these equations are now converted into algebraic equations. Now, these equations along with the network equations will have to be solved. We will do this thing in the next turn. Now, today let me sum up what we have studied is that we have studied the basic concepts of dynamic equivalence, and we have also studied that the dynamic equivalence can be obtained using a linear model and considering a classical representation of synchronous generator. Okay, thank you.